Happy Monday, Ace Trick students. Mr. Renier back here. I hope you had a nice weekend. Good Mother's Day. Today, we're going to talk about graphing these polar equations, more elaborate graphs, I would say. Fairly short and simple week I have planned, and next week, really our last 2 weeks of school. I understand many of you are starting your AP test this week with chemistry and world history and statistics, etc. So I don't want to eat into that time. So today, short lesson I have planned here, graphs of polar equations. We are supposed to be able to do these by hand, which means, use a T-chart, sketch them out without any graphing utilities. And also you're supposed to be able to do them with a graphing utility, whether that be your TI Nspire calculator or Desmos. I'll show you that on Wednesday, since maybe we don't all have a calculator handy at home. Both of these things, I definitely want to make sure we get in this year because they are utilized in Calc 2, which many of you will take your senior year. After you take Calc 1 next year, your junior year. But neither one's all that difficult. So graphs of polar equations. First off here, I'm not going to run through this large example that you see in the middle of your page. We're going to kind of somewhat ignore that this year. But in its place, I want to review and reiterate something I hit last week about your two most basic simple graphs. I'm going to just kind of add those on here. So I'm going to say let's graph r equals -2. And also, I'm going to say let's graph theta equals -pi/6. So on, I believe, Monday of last week, I discussed how if you're asked to sketch a curve of a simple r equals, and that's all that's going on, curve, r equals -2, that's going to give us a circle, because we color in everything around the second ring. And even though it's negative, it's still going to be a circle, because we've discussed how negative radius just means you move away from that angle. So in essence, it's a circle kind of moving in the wrong direction, moving backwards, but when it's completed, it still forms a circle. The fact that it's negative might become important in calculus when you talk about specific directions happening. But as a picture for us, just realize r equals -2. We make a circle going around the second ring of our polar coordinate system here. So in red, I have r equals -2. And then we discuss theta equals. A simple theta equals without an r mixed in always makes a line, because we just find this angle of -pi/6. Again, 0, or this would be radians, but 0 is always the positive x-axis, which is called the polar axis in this polar form. Negative means instead of moving our normal up counterclockwise direction, we're going to move down and clockwise. And -pi/6 is kind of that second rung on this circle. And anything along that line becomes our solution. And then we discussed last week, this does not stop at the pole, because again, that negative radius lets you kind of go the other side. So I want to take this and extend it all the way through. So that is theta equals -pi/6 in purple. Theta equals makes a line, r equals just a value makes a circle. The more interesting things occur when we start mixing r and theta together. And that's what we're going to get through on example 2. And that's all we're going to do today, just example 1 and example 2. We want to graph r equals 3 - 5 cosine of theta. And this is not just a simple line or circle, because I have an r and a theta kind of mixed within one equation. To do this by hand without utilizing a graphing calculator or Desmos to give us a picture, we need to go through a few things. You're going to have to, unfortunately, create quite an elaborate T-chart to make this an accurate looking curve. So we want to set up a T-chart. We're going to find our radius values. And when we're done, I recommend you connect the points as you go. And I will emphasize that as I work that out. So it doesn't make a lot of sense as I say it here. So connect points as you go. As far as the T-chart's concerned, it needs to be, you need a lot of points to make an accurate picture. There's a lot of things that can go on in these polar curves. So I'm gonna have a theta column and a radius column. And rule of thumb is, let's use our unit circle values. So for instance, 0 degrees, 30 degrees, 45, 60, 90, 120, 135, 150, 180. And I'm kind of out of space. I'm gonna make another kind of column to this T-chart and go all the way around our circle. So after 180 comes 210, 225, 240, 270, 300, 315, 330. We want to finish this up back to the start at 360. It's a lot. There's a lot of points there. To find these, we need to take our 0 for theta and plug it into our equation of 3 minus 5 cosine of theta. And that's kind of why I had you get r by itself when we did equations last week. That tends to be the form in which things are easier to find points and to plot. I might write this out completely here. That's 3 minus 5 cosine of 0 degrees. This would be 3 minus 5 cosine of 30 degrees, on and on and on and on. I'm not going to write all these out. You would go to your calculator and literally first make sure you're in degrees, which I have this set to degrees. We can just type in 3 minus 5 cosine of 0. I want this to be in decimal form, so I'm going to put a decimal after that 0. That way I don't have to hit Control Enter. And we're going to get a -2. I'm not going to do every single one on here, but again, another one, 3 minus 5 cosine of 30. I'm in degree mode, so 30 degrees gives us about -1.3. Now I would say round to a tenth to be somewhat accurate. Maybe one more, 3 minus 5 cosine of 45 is -0.5 roughly. So I found already, let me change colors here, 0 degrees gave us a -2, 30 was a -1.3, 45 is -0.5. And I've already done all these. I'm going to check on my paper here. 60 degrees, if you can continue this process with your calculator, would give you 0.5. 90 degrees gives you a 3. 120 is a 5.5. 135 is 6.5. 150 degrees is 7.3. 180 degrees is 8. 210 is 7.3. 225 is 6.5. 240 is 5.5. 270 degrees is 3. 300 degrees is 0.5. 315 degrees is -0.5. 330 degrees is -1.3. And 360 is equivalent to 0. It's kind of back to the start. That's a -2. So those are all the radius values one at a time. A pattern did develop here. If you notice, we went -2, -1.3, all the way up to an 8. When we got to 180, it then worked completely back down that line, 7.3, 6.5, all the way down to -1.3 and -2. Because trig values repeat pretty consistently, patterns are very common when getting these T-charts and these curves moving. It's not the same pattern every time, but you can usually pick up on some type of pattern developing. It's just not going to be maybe this pattern that we see on this particular problem. Now we want to plot these to get our curve. To kind of help myself, I'm going to label my angles on this. We got 0, skip the first one. There's your 30, 45, 60, skip 1, 90, skip 1, 120, 135, 150, skip 1, 180, skip 1, 210, 225, 240, skip 1 is 270, skip 1, 300, 315, 330, skip 1, and 0 is 360. On this particular problem, to make it fit on this curve, I've said let the polar axis scale be 2. That just means that every ring represents a radius of 2. So you have the pole is 0, and then 2 for the first ring, 4 for the second ring, 6 for the third ring, 8 for the fourth ring. And I did that because I can see my radius values go out to 8. And if I went a scale of 1, it wouldn't fit on this particular coordinate system plot that I have. Now, we want to plot these points one at a time. This becomes the tedious work. But if we go to the 0-degree angle, which again is the positive x-axis, the radius of -2 means I move away from that. So I'm actually going to move towards 180. My first dot is off on the left where I put the blue dot. There's -2, 0. And then 30 degrees. Again, look for 30 degrees. The radius of -1.3 takes me away from 30, really towards 210, and kind of between the pole and that first ring. Maybe somewhere in there where I put that second blue dot. And I always say connect these as you go. A lot of times on these, they're quite elaborate and they kind of intersect and cross several times maybe, and you could get lost at the end trying to connect these dots. So I'm going to connect them. 45 is -0.5, so 45-degree angle. Go away from that because it's a negative. -0.5 is pretty close to that pole. Little dot I kind of put there. Connect these points. And then 60 finally crosses into the positive territory. 60-degree angle. Move towards that 0.5 units because it's a positive. So on the other side of the pole, connect these. And then 90 is 3. So 90-degree angle, move towards it, +3. 3 is between the first and the second ring. There's that dot. Connect these points. And as I kind of connect, I go back and kind of smooth it out because these are always curved. They're not going to be straight lines necessarily. 120 gets you to 5.5. So 120 angle, 2, 4, not quite to 6, 5.5. Connect that. 135 is 6.5. So 135, 2, 4, 6, a little bit beyond 6. Connect. 150 gets us out to 7.3. So not quite to 8. And then 180 is 8. So 2, 4, 6, 8 on our fourth ring is a radius of 8. Connect. That's halfway around. From there, 210. 210 is 7.3, so not quite to that fourth ring. Connecting as I go. 225 is a 6.5. 240 is 5.3. So again, inside that third ring. And, or excuse me, 5.5 I meant. And 270 is at 3. So that's between the first and second ring. Bringing me back in 3/4 of the way there. 300 is 0.5, so 300-degree angle. 0.5 is really close to that pole. 315 dips back into the negative. So 315 is in the fourth quadrant, but -0.5 radius tells me to move away from that into the second quadrant, opposite. So this curve is going to cross through the pole, connecting to my dot. 330 is a -1.3. So again, 330 is down in the fourth quadrant, but -1.3 tells me to go away into the second quadrant. a little bit closer to that first ring, connect. And finally, 360 gets me back to the start at -2 and kind of finishes this loop. So we got a picture, kind of like that. It's common to have these things looped. Like I said, you will do this in Calc 2. There are reasons for this. This particular curve has a name. It's called a limacon. It's one of the 5 classical curves in polar equations. We'll talk about those more on Wednesday when we get graphing calculators or Desmos out. Then we'll talk about how we can, make a helicopter propeller, a rose, a flower, a heart. All kinds of shapes can be formed with polar equations. Today's assignment is short. There's not real, I don't know of a great way for you to do this and submit it to me on Schoology, so I'm going to trust that you do it. I have a small 3-problem worksheet. 2 problems are the very basic curves from up top, r equals and theta equals, and then one that you need to make by hand with a T-chart. That's going to be somewhat intense, like this example was here. Do that, check the key, make sure you do it correctly. If you're having an issue, let me know. Wednesday, we'll have a video on how to use your calculator or Desmos to make these happen. We'll talk about the classical curves. There'll be somewhat of a Schoology assignment on Wednesday. And then Friday will probably be just a small quiz again over your graph material. All right, hope you're all doing well. Let me know if you have any questions. Have a good day. Later.